we're going to go delve into more complex data representations consisting of arrays and objects. So you all have just experienced the labs. I'm sure, was there anyone that wasn't in the labs? Awesome. I'm not surprised that the people that are in here in the class were also the ones attending lab. Good job. So objects and arrays. We'll start with arrays today. And so the big question that arrays answer is, what if you had a collection of objects that were all the same type? Like stones of different weights. How can you work with this data efficiently? So before arrays, if we wanted a bunch of things that were like each other but had to have slightly varying values, such as their weight, like if you wanted a bunch of circles of different radii, and you wanted to sort of like be able to parameterize those and use those, you'd either just write the number of them right in you'd either hard code all the values for their weights inside of a few lines of code, or you would pass a variable to a function which would then draw the stone. But that still doesn't solve the basic problem of, if we have a ton of stones, like 100 stones, that all need their own weights and all need to be respected individually, how do we do that in sort of a sane way? How do we do that in a way that doesn't really overtax our authoring resources, make our code huge, ugly, and bloated and error prone? Like we would if we had a bunch of lets with a bunch of stone weights. Stone weight 1, 2, 3, all the way through 99. Or 100. That would be burdensome. Here's where we enter arrays. So arrays are indexed lists of items. That is an artifact of an old age. I thought I got rid of that. I must not have gotten some of these slide changes in, pardon me. That was the case in Java. So arrays are identified by name and an index. Just as we talked about in the lab, if we had an array with a variable name of A, it has a whole bunch of boxes that could be associated with it, a whole set of boxes, an array of boxes, if you will. And to get to each one of those boxes, you use what we call indexing. And the index starts at 0. So the first box associated with A is index 0, second box is index 1, third box is index 2, so forth and so on. And the note that I had up here about the values of the boxes all being the same type, that was an artifact in Java. Java is a more strongly typed language, and you had to say all of the boxes are numbers, or all of the boxes are strings. Right? So you couldn't be flexible. In JavaScript, we can stick whatever we want inside the boxes. It's really nice and wild and loose and hairy. Here's an example of our stone weights. Let stone weight equal to this array, and this is how you can give initial values to the array. You just put them inside of those curly braces, inside of these square brackets. Square braces, there we go, jeez. Square braces that we use for beginning a new array. So if you want an empty array to start with, you just give it the square braces without anything in it. If you want to have your array have some initial values, you can use something like this, like the value 3, 54, and 7, separated by commas. And so when we go into our indexing, we can see that the stone weight of the 0th index is 3. Stone weight of index 1 is the value 54, etc. And you can use them like you would to every other variable. You can assign to them, and you can use them in math expressions. So 6 plus stone weight applied to 2 would take the 54 from stone weight 1, add 6 to it, to a value of 60, and place that in stone weight 2. So the 7 up here would become 60 as a result of that line of code. Okay, I'm assuming this is a review. I'm hoping most of you are with me at this point. Am I getting good with me's? Yes, excellent, thank you. Right, so this is an optional initialization step. You can put stuff in it or not. The general form of declaration is a name equals square brackets. Of course, the let, just like every other variable name. If you have yet to declare that name, you have to put a let or a var in front of it. So let's example, let list. List in this case gets an empty array. And arrays, they can have a dynamic size. So this is great. Not all languages do this. For instance, Java, if you use processing, you have to declare the size of the array when you first initialize it. So we're lucky here. We can push, pop, we can have sparse arrays, which means there doesn't have to be values in every single array location. We have a lot of flexibility here. So let's take a look at an example called color arrays. So this is what the example does. We have some rotating colors. And we pull this off. Let me make this just slightly big. It's hard for me to tell. I see such a tiny screen and you see such a big screen. So the first thing we do is we initialize an array, an empty array, and assign it to the name ball color. So ball color is an empty array now. We have a count variable at 0. We have a diameter equaling 100. A setup function where we create a canvas of 400, 400, give it a background color, set the refresh rate to 30. Give 3 different ball colors inside the array. So array index 0 gets this bluish color. The purplish color gets into array 1, index 1 of ball colors array, and the orange color gets into index 2 of the color array. So in our draw command here, what we're doing is every 10 frames, so we're looking at our frame counter, looking at the frame count, every time it's a multiple of 10, exactly, so frame count mod 10 being 0, we increase the count. So every 10 frames, we increase our count. We'll see what that does in a minute. So here we are just filling. The first is the top 3 balls that do not change color. The first one uses the color, the first color in the array, and draws a circle of diameter at 50 of diameter size at 50, 100. The next one is the second color in the array, or color index 1. And the third is even more, is moved to the right even more, and it is using the third color in the index, or the third color in the array at index 2. Now the second set of circles, the 3 on the bottom, they change color over time. So what we're doing is we are taking that count that we're increasing here, and we're taking it mod 3. So if count mod 3, so we're using the result of count mod 3 as the index into the color array. And because it's mod 3, we know the value will always be 0, 1, or 2. So this count is helping us cycle through the indexes in our arrays. Now here, we just offset it by 1. So it will always be like 1 more advanced in count than the one above it. And the one below it will be even 1 more advanced past that. So they're all going to have their own index into this color array that we have. And this is how we get them rotating colors. And the colors, the indexes are sort of moving so that it looks like the balls are traveling to the left. The colors are traveling to the left. All right, does this example make sense? Is there anything I can explain, help clarify? I know we are using mod, which we just sort of like really learned about last time. And we're using here something a little more advanced than we had talked about in the lab for our index. But basically, all you need for an index is a number, a whole number. And that will get you into that index in the array. All right, there's our color arrays example. Array length is interesting. So you can use the dot length property, which is inherent to any array. And it also is .length is also accessible in other structures, But for array, it gives us the number of elements in the array, the number of boxes in our array. So here, if we have an array that we initialize to have the values 10, 11, and 12, at indexes 0, 1, and 2, what would the length be? What would this print? I'll take the number of fingers. 3. Right, there are 3 items in the array. So the length is 3. So something to note here is that length is a little weird. Usually when we have something that acts upon an object, it's a method. It's a function. You have to put parentheses behind it. Length is a little weird in that it does not have that. So length, you do not use big parentheses after. It is a property, not a function. All right. So these questions are a little basic because they're adapted slides from last year when we did this lecture before the lab. But you should know that the value of a.length is 3, like we just talked about. The index of the last element in the array is 2 in this case. But what would the last index be in any case? Is there a little math statement that you can give me, a little bit of arithmetic, using array.length to give you what the index of the very last item is in any array that's greater than size 0, length 0? So 10 is index 0, 11 is index 1, 12 is index 2, and the length is 3. What's our little handy little formula here? It's length minus 1. A.length minus 1. So anytime you want to address the very last thing in an array and you don't know what exactly the length is, you can just say length minus 1. That will get you the very last element. It's kind of handy. So a.length. What is going on here? What did I... Okay, those are wrong. The length is 3... 2. Whoops. All right, I was working with another example earlier. My bad. I can see why people were giving me the wrong sets of fingers. So they were looking at the slides ahead of time. Okay. Now there are a few ways to grow arrays. You can copy an array to a bigger array. You can allocate a larger array and copy it first, but we have some methods that JavaScript gives us to make this a little simpler. We have a bunch of functions help us manipulate the array. Shift removes the first value in the array and makes the array one shorter. Unshift takes a parameter and pushes that parameter into the first slot in the array and makes it one longer. Push adds an element to the end, like we did in the lab. And pop removes an element from the end, making it one shorter, length one shorter. Splice is interesting. So splice takes 2 numbers. The first number is the index, and the second number is how many to remove from it. Right? So if we wanted to move the middle item of a length 3 array, like if we wanted to remove the 11 out of this, we'd say a.splice 1 1. So it would remove, it would start at index 1 and remove one item from it. we could remove the 11 and 12 by calling a.splice1, comma 2. And then we'd be left with an array with one item in it with a value of 10. You could also sort arrays. So JavaScript knows how to sort basic things like numbers and strings. With strings, it sorts them in alphabetical order. With numbers, it sorts them in standard number order, in ascending order. You can also call reverse on your array, and whatever configuration it is, it'll flip all the indexes around. The first thing will be the last thing. The second thing will be the second to last thing. It'll just reverse the order of everything in the list, which is kind of handy. You don't have to do this yourself. It's kind of tedious to write a set of for loops to reverse all the items and copy them around. Sometimes that's an assignment in early programming classes. But we can make pretty things instead. Now let's take a look at a better way to iterate through our loops. So we had our example previously. Why did this go all the way up here? So we had our lab example where we iterated with this for loop. And we had to manage a bunch of i's and use a bunch of indices and things. I gave this to you to sort of like expose the indexical nature of arrays, but there's actually a much easier way to do it, which I may have used on hindsight, I may use in the future. It's a variation of the for loop. Where here, we have a set of locations. 50, 100, 150, 200, 250, 300, 350. We create a canvas. We draw the background color as salmon. We set stroke, we turn off stroke. We set the fill color to turquoise. And here's our new type of for loop. It's a for of loop instead of our for loop. So the difference here is it does a lot of that boilerplate for us. So for, and then we need to set, the parameters of the iteration. Here, it's interesting. It takes a first thing, a keyword, the keyword of, and then an array. And so what happens here, and I made a let location here of locations. What it does is for every item in the array, it goes through the loop one time. And what it does is the first time through the loop, the variable that we have here, location, gets the first item in the array. The second time through the loop, you get the second item. Third time through the loop, third item. Fourth time through the loop, fourth item. And it does this and knows how to not go over the end of the array. So this is a nice, easy, clean way to go through an array and make sure you hit every element in a way that's a lot cleaner, right, than with using all the index operators. So we could go to lab for, whoops, I have to click fork. We can fork this thing with for of. Let's see if we can modify it on the fly. So instead of all of this, we can do for thing, let thing in falling things, draw image, thing.image, draw it at 250, lie location thing.y, and then 25, 25. Then we can do if thing.y is greater than 750, thing.y is equal to 50. Then we can do thing.y plus plus. Let's see if I did it all correctly. Nope, I didn't. What did I do? What did I mess up? Oh, I see what I did. I see what I did. I got a little ahead of myself. I'm sorry? Oh, yes, I use a different syntax from the language. Thank you. The whole point. There we go. Now, what do you think? Is that code a little easier to read? Does it make more sense now? But what you should know is that there is index happening under the hood. The indexing is still very important when you're dealing with arrays. Now look at the example rect array. I'll just show you a little slightly more complicated example and something fun to go along with it. Here we have just a set of animated rectangles. They're all managed in an array. They all do different things. There's a bunch of operators going on here. I have a little slider bar I put in where you can change the scale of them. Whoa. And the slider bar is actually really easy to put in. We'll see the code for it. Okay, so we have an array of the lengths of the square, so the sizes of the square. We have a scale variable and a slider. Scale set to 0.5 and a slider. Make a canvas, put a background color, frame rate 20, turn off the fill, rect mode to center. And here what we have are the sides of all the rectangles. So what is sort of like the width and height of the rectangles? That's sort of represented in these size variables. So the 0th one is sized at 40 times whatever our scale is. And we can change that scale number with our slider. 30, 50, 10, 19, 27, 15, and 4. So all of our different squares have different lengths, just as if our rocks had different weights. And here's a simple code for the slider. Create slider. What's the minimum value of the slider, maximum value of the slider, initial value of the slider, and how much does it change in each increment when you slide it? Then we want to put it somewhere and give it a size. Unfortunately, it's a little weird. It doesn't actually respect the canvas in its sizing. It does like this entire window, so it's a little bugged, but still kind of fun. All right. So this is an example here that I don't want to work through all of these problems in here, but it just has this example has a bunch of little complicated conditionals and a bunch of different ways we're using the array and doing math with them and using the indices. So here, this is something that you can use as a bit of a study guide. If you can predict the values that will be placed in the array at the end, then you'll be doing really well. You'll have understood arrays quite well. So complicated example with study guide. It's a little contrived, but it is useful. Right, so we're doing, it's a little animation based. So when the frame equals 20, we sort all the squares by square length. So if we see it here, we'll see 20, but in a third of a second in, all the squares get sorted. Bink. Using our sort function. There it is. Then, between frames, when the frame is greater than 30 and the frame count's less than 55, we change the index 7. We reduce it by size 2. And we reduce the index 5 by 1. So they change sizes a little bit. They reduce in size. If the frame count is exactly 65, we sort them again because now they've changed, right? So here, 1 second in, they'll change again soon. And I guess that's a little longer than I thought it would because the frame rate is 20. So each frame is 20 seconds. So that's 4 seconds in, they get sorted. Oh, I'm sorry, 30 seconds in, they get sorted. we add another square length to the array. You can also append to square length and add it to the end. It's a slightly different function. I'll give you documentation for it. Basically, what append does is it takes this this array, adds another, it basically pops or pushes another value on the end, and then returns that new array. And then we catch it and put it into this variable name. So this technically, append makes technically a new array. All right, when frame rate is greater than 95, and if it's less than 95 plus a scale value, so we're actually using our scale value here in the timing of the function, we take the last item in the array and we make it a little bigger. All right, so that was just managing values in arrays, all of those if statements. And then finally, we draw them all at scale. We draw them all with the x value of 60 times scale times 50 times I, so they're all spaced apart evenly, but scaled. Take care, have a good one. The y value is scale times 30. Let's just get rid of you. Get out of here. There we go. And we use the lengths for the height, for the width and height that we have in the array. Right, so there's a bit to work through here. I'd encourage you to look through this and make sure you understand what's going on. If you can handle this well, you probably have a good idea of what's going on with array. You can also have two-dimensional arrays. So we said we could put just about anything inside of an array. Well, it turns out you can put arrays inside of arrays. So each one of these indexes can have a whole array of their own. And you can even initialize it like this. So the very first index of A2D is an array consisting of 1, 2, and 4. The second index of A2D is a whole array consisting of 5, 1, and 7. And then it has an index 2, a third thing in A2D, which is also an array of 2, 9, 18. And what happens is when you go into an array and you pull out one of its indices, that's just a whole new data structure you can use. And here what we're doing is saying, okay, A2D, we're treating you as an array, and we're going to try and pull out the first index 1 value. I should say index 1 value. Okay, out of that thing we just pulled out of A2D, we're going to treat that thing as an array as well. And we're going to try to pull out the second value, index 2 value from it. So let's take a look at this. Index 0, index 1, index 2. Okay, we have index 1. That's the middle one. Awesome. So inside of this one, we want to pull out index 2. Okay, index 0, index 1, index 2. That's 7. Right? So you can nest this as much as you like. You have 3-dimensional arrays, 4-dimensional arrays, 5-dimensional arrays. You can simulate quantum foam, I guess. I'm not sure. Probably be a little past what your browser could handle computationally. But the thing is, we have flexibility. Like if you wanted to make a chessboard or checkers or whatever, some sort of gridded board, very easy to do here. You use a 2D array that's where the length of the outer array is the length of tiles you want, and then so it's sort of like the height of the board, and the width of the board could be the length of all of the inner arrays. And then once you want to like look at a position, like you go down, you want grid 2, you want row 2, column 5. All you have to do is put 2, 5 in here into the 2 index slots. Great. We have an easy way to index positions in our like sort of like our tabletop grid space. Uh-oh. Are we losing internet? Okay. I did remove the rest of the slides. So this is what I wanted to cover with you with arrays today. So this is array part 2. Do you have questions about arrays? I know we went slowly, did some review at the beginning, and there's a good chance to check your phone there. And then we got to some more complicated things at the end where luckily you all gave me a lot of attention. Thank you. And then we got to this place where we learned something new today where we're talking about 2D arrays, which are something that I want you to like look at the form of and be able to index into, but I don't expect you to write these, particularly for the midterm. All right, questions about arrays. How are you feeling about arrays now? You feeling a little bit more empowered than you did when I threw them at you at 8 a.m., 9 a.m., or 10 a.m.? Good, good. That's the goal. We're giving you tools here to do interesting things in the world with. All right, and so you see all of these blank slides? These were all of the object slides. I really wasn't feeling how they worked. So I went another route. So arrays, the entire set of array slides and presentations is in a sketch. So we're going to look at, arrays. Objects are all in a sketch. So we're going to talk about objects and object-like things, including classes in JavaScript. So to follow along with this, just open the sketch. Feel free to fork it if you want to play with it. Have your own copy. Let me just 100% check to see that I made it available. Yeah, okay, so it's just this last one here, objects inside of our collection. Okay, let me do a little configuration since I haven't used this with this format before. Okay, so we have the thing we want to run on the side. We have what it looks like. We have the code. I'm just gonna have to make the text a little smaller, I think. Is it still readable? Folks in the back like this? Okay, good. Yeah, I love a large screen. This is way better than the lab. And is the code readable? Legible? Excellent, thank you all. So creating an object. So you should treat objects sort of like blueprints. That's where we're going with this. They are collections of useful things together. They're an encapsulated bit of data and functions. So we'll look at that a little bit as well. Like this ball here. So a ball is a collection of an X value, a Y value, and a size. Right? All that's meaningful to a ball. All that should travel with the ball. Whenever you want to use the ball or send it to a function, you can just send the ball over and all that stuff comes with it because these X and 200, Y and 150, and size and 50 are all values, properties, tucked inside of that object. And eventually we're going to use this as cookie cutters. We're going to have a way we can define objects like we define functions and then be able to reuse and make new versions of the objects later. That's what this concept of classes is. And we'll give you examples of that. So in this code, this is the syntax I didn't show you during the lab, but here is how you initialize an object with some values. So when we used it in class, we just used empty curly braces, right? And you can do that. You can give yourself an empty object. But here we give ourselves an object with a ball. So X colon 200 gives it a value of a variable, like a property of X with a value of 200. And then we give it a property of Y with a value of 150. And we give a property of size with a value of 50. And we can see those in here. You can see the print ball down here. You can see that we have the ball is an object with an X value 200, a Y with a value of 150, and a size property with a value of 50. And down here in the draw function, we're using it. First, we're drawing a background. Then we are using the properties of our ball in the draw call. So circle, the first two parameters are X position, Y position, the X position, and the Y position is the second parameter. Third parameter is the diameter, or the size of the circle. So we're pulling out the ball.x and using it as the X position. We're pulling out the Y value from ball and using that 150 as the Y position. And then we're pulling out ball.size, which is 50, and using it for the diameter of the circle. I'm hoping through the lab, you're fairly comfortable with that bottom line. This should make sense to you, but should be like just a slightly new syntax for you. And luckily now you have it right there in your nice studyable little sketch that you can follow along with. All right. So just want to make this very explicit. You can access properties of an object. Part of why I sort of like repeated this is because I want you to sort of like get some of the nomenclature down. Objects, the things inside them, are properties. Properties have a key and a value. So the property X, the key of it is X, and the value of it is 200. And there's a couple ways to use this. So we use the dot notation here. You can actually use this array-like notation here. And what it does is it looks at the string you give it and says, okay, does this string name match any of the labels inside of our object? And this is kind of neat. So when you print out this, when we print out ball, you see how these are actually strings? So the property names are actually stored in a string-like form inside the object. That's how JavaScript handles them. And that's why this syntax works. So basically this ball.x and ball square bracket quote y quote in square bracket, these two mean the same things. Just like x plus plus means the same as x plus equals 1 means the same as x equals x plus 1. Right? They're just a different bit of different syntax that means the same thing. And so you get a nice little handy shortcut here. I consider these, shortcuts. Is a little less typing to do, and it's a little handier to use. So those are two ways to pull properties, values of properties out of your objects. And you can see here, ball.x is 200. Ball, the value of the label y in ball is 150. All right. Okay, we're getting somewhere. We call this bracket notation and dot notation. You modify the values inside of properties with very much the same way. So this is just a reflection of the accessing. So we can set ball.x equal to 250. We can assign the label of x inside of the ball object to the value 250. We can assign the size key inside of the ball object with the value of 60. And when you print out ball, you can see that those did indeed change. We actually refreshed it, still had the last, there we go, the last stuff in there. So now y is 250 and size is 60 instead of 50. All right, adding and deleting properties. So we sort of like fuzzed over this during the lab, but this is one way of adding properties, doing it in the initializer. So adding x, y, and size. Well, you can add things at the same time. So if you have this notation here where you say ball.color, and notice ball does not have a color initially. But if it's on the left-hand side of an assignment, it will take whatever's on the right-hand side and use that as a value and make a new property, add a new property to the object of this name. So now, after you run this line, ball would have a new property, and its key would be color, and its value would be this string, rbg2 left paren 255, comma 0, comma 193, right paren. And there's the delete keyword. A keyword just like for, if, else, of, function, return. Delete looks at an object and removes a key and value from it by name. So what we're doing is we're removing ball.size. So now size is just gone. We've removed it from the object. We've excised it. So let's take a look at this. Refresh first. Got to remember to refresh first. All right, so now down here, we have an X value, a Y value, and a color. We've added this new color, but that's it. There's no size now. Right, so this is how you can extract values, add values, modify the properties of an object. But did you know? JavaScript's flexible. Objects can hold lots of things. Did you know a function was a thing? A function is actually something that you can pass around like a variable. Right? So here what we're doing is we're giving our ball a key called display. And display, it's getting this function. It's getting the declaration of a function. It's not running the function now. It's like storing the function inside a variable. And notice there's no name to the function. This is an anonymous function. We're not going to go deep into these. But basically, it's a function with no name. Normally, you couldn't use these. But because we can use functions as objects, the function that gets created by this is just stored in display. And so display is the new name for it. And we use it down here. We can call ball.display with parentheses. So we're saying here, ball, do you have something called display? Okay, if you do, let's treat it like it's a function and see if we can run it. That's what the parens after a name do. They say treat the thing to the left as a function. See if we can execute it. And this is a function. And it sets a fill color and then makes a circle. Right? Now that should be a little weird, right? But it's also kind of interesting and powerful because now when you pass the ball around, you can pass around its capability to call functions on itself as well. And an aside here, there is a web concept called monkey patching. And what you do in monkey patching is like you have all these functions, but let's say it doesn't do everything you want it to do. What you can do is make a function inside of an object and then store the previous function, the one you want to fix, in it as well, but hide it in some variable. And so when you call the function that you want, the function that was sort of like the renamed version of the old function, it'll do whatever it wants and then call the old function whenever it wants as well. So it can like do something like do some security logging and detection, then run the original function, then do some cleanup afterwards, right? But still look transparent, still look like the old function to all the code that's using it. That's a little high level, but monkey patching. I will not ask monkey patching in the exam. That was definitely a digression. And so something that we're actually also doing is using the this keyword. We'll explain the this keyword soon, but basically what it means at the high level is whatever name we have after it, it has to be a property of the object. So objects can have functions together. Functions and data. They can store values and use functions. That makes them pretty powerful. You can use multiple objects for multiple shapes, just like we did in the lab. So here we have two circles, one slightly bigger than the other at two different locations, which we use here, right, with two circle calls. This should be a pretty straightforward extension of what you know so far. Much less of a digression or an extension than functions inside of objects were. Now we can loop through objects as well. So let's just close this just for a moment. We have a ball object. It has an X, a Y value, a size. It has all these properties, size and display, excuse me, which is a function. Pardon me, I just whacked the microphone. What we're doing here, we're using for and in. See, this is why I got confused with in, because this is another way you can use a for loop. Of is for arrays, in is for properties of objects. And what this is doing is it's letting key be the key of the object. Like we're getting all the keys out. So we're looping through we're doing this loop once for every single property that the object has. X, Y, size, display, and then, we can print out the value of that key. So let's take a look here. So we're going through. So in order, X, we're printing X, colon, space, and then the value of whatever the key is. So key is X in this case, colon, space, concatenated with whatever value the key has. So whatever, so you can replace this. This looks like X. That's what it would be the first time through. So here, key, colon, space, value. Y, colon, space, value, 150. Size, colon, space, value. Display, colon, space, the source code of the function. It printed out the source code for you in print. Right, that's kind of interesting, right? Let's pull this up just a little bit so you can see a little better. So objects are weird and powerful, right? This is probably not what you expected this to be, right? But that's what it is. That's how it's treated. So when you put display with parentheses after it, it runs this stud thing as if it were a function, which it is. Okay. So here is where we're going to be a slightly more text heavy. This is where we're going to talk about class-like things. So how many of you heard the term object-oriented programming? Okay, a few folks. So what this means is that this is an idea of your code being broken down into what we call objects, which are little packages of properties and functions, properties and methods. So for instance, if you had, we'll go with the classic example, a vehicle. What are sort of like properties of a vehicle? Color, size, engine size, make, model. All those things are sort of like properties of the car, things that are like static, right? They're a value. But what can a car do? Accelerate, brake, open. Well, I guess brake in two senses if you're talking about Cybertruck. It can flash lights. It can run wipers. So all these are actions that a car can do. So a car, we're treating as an object. So what we're doing with object-oriented programming is treating things in that sense, that they are objects in the world that have attributes or properties that are sort of like static, like size, color, that sort of thing, and things that they can do, actions they can take. Accelerate, brake, run wiper, flash headlights, right? And so those things that they can do, those are functions in this world. So the fact that we have a ball that can display itself on the screen, that's kind of neat. The ball can draw its own graphics. You could also have a function that handles what happens when the ball hits the ground. How does it change its movement after that? You could have a bounce function, a reflect function. All right. So the idea here is that we want to have a definition for what an object is. So this is like a cookie cutter, not a cookie. So here, this function ball that has all this stuff in it, this is the JavaScript syntax for creating a ball class. So if you this code here, it doesn't do anything. Just like when you define a function, it doesn't do anything until you call the function. A class definition here, an object like class, doesn't do anything until you do something like this. Let my ball equal a new ball with these parameters, which get mapped to these parameters. Right? And so what this does is it creates a new object for us. And the object has these values. It has an x, which gets the incoming value of x. It gets a y, a key of y, which has the value of the y coming in. It gets a key of size, which has the size coming in. And it gets the key display gets this function attached to it. Right, so that curly brace function, the curly brace stuff that we had before, right here, is sort of like this makes these curly braces make an object that has all these things in it, right? Well, this is a way to give that sort of structure a name. We call it ball. And we could say, hey, I want a new one of those. So we use this. We can give it whatever parameters we like. And so now we can have balls of all different positions and sizes that all conform to this like spec. There are different flavors of cookie dough within that same cookie cutted, put in the same cookie cutter. And we can call the display on it. So I encourage you to read the text here. I basically talked about what is in here, but the text is another example. I designed this so that when you're looking at this later, there's a lot of explanation to go along with what you're seeing. Now, that was sort of like the old school way to do it. If you look in like a bunch of Java textbooks, that was like the way to make classes in Java. But in the last few years, we've made our lives better in Java. Now we have something that looks a little better. We can make a class ball. So now class is a new keyword we have. So instead of like having this weird thing that kind of looks like a function, you can use this instead. And the constructor, that's the thing that's called when you use it with the new keyword. This is the thing that actually starts the object creation process. So just like we had the function up here taking an x, y, and size, here we have the constructor taking an x, y, and size. And this keyword is now important because now we're in like this is a blueprint, right? A cookie cutter, a thing that isn't a house, but you can make houses with it. So whenever you make a new house, the constructor is saying, okay, this house, this object that we're making has a value, has a key of x, and that gets its value from the incoming x value. So you could call these like x1, y1, size1 to disambiguate. Right? So these variables are not the same thing. This is why we have the this keyword. And JavaScript knows how to tell the difference between them because this .x is a thing in the object, and the x that was coming in here was defined and coming in through that function. It's a function declared variable like we've used a bunch of times. So they're actually two different boxes. So the this keyword helps you. It says, okay, we have like all these places we can store boxes. The box that we're talking about is the one that's inside the object. So this side x is the one inside the object. The other x that's coming in is function local. It's coming in as a function parameter. There are two different notions of x's here. And you can have a lot of different notions of x's. Right? You can really make this complicated. You can let x equal 100, 1000 up here. So now we have three distinct x's, all existing at the same time. Since this one's sort of global, we have the x that's coming at this value. We have the x that's inside the object. And then we have this global x outside. Right? So this is why using repeated function names is a little bad, or repeated variable names is bad, because you can really confuse yourself. But this is convention. Like if you're going to have a property of x and you want to initialize it with some property, you can keep these the same because it's by convention we know that this x, y, and size, and by JavaScript's parser, how it interprets your code, it knows the difference between these. All right. Now, inside, this is still inside our ball. See how they're highlighted? The gray highlights? The ball is everything from here to line 11. And so we're also making a new function. Giving it the name display, showing it it's a function by, oops, not dragging a bunch of stuff, by giving it open parens, and then we're giving it curly braces for the code that's associated with the function. So looking how this is used, we have my ball equals new ball, and we're giving it the 3 parameters, the x, y, and size. All right, so this new keyword is saying, hey, is there a class or a class-like thing called ball with a capital B? And so new looks for one. Turns out we have one in our code. It's like, great, awesome. Does it take 3 parameters, 200, 150, and 50? Hey, look, there's a ball with a constructor that takes 3 parameters. Awesome, we're off to the races. Let's make a new one of these. So 200 gets mapped to y, 150 gets mapped to x, 50 gets mapped to size. And then inside we have first line of code takes that 50 from y and places it in a new x that's inside that new ball object that we're making. Same goes with y and size. And so now if we print this thing, actually we have it in, yeah, we'll just print it in setup. Print my ball. Refresh it. Look at what comes out. We'll see that we have a new object that is in the shape of a ball. It's got x, y, and size. So when you just print things, it doesn't print the functions, it only prints the properties. But if we went through and did the for in loop for each key, we would see that the functions are there. All right. So the last thing here is more practical. The others were a little bit conceptual, something that'll help you out in the future. This one's a little more practical. We're going to show how to use this class structure to deal with animation and to make our lives a little cleaner. So first thing we're going to look at here is that we have a ball that moves at half a pixel a second, or half a pixel per frame, going across the screen. Very sedate. And this definition of ball is close to what it was before. So we have x, y, and size in the constructor. This dot x gets x, this dot y gets y, this dot size gets size. We have a display function, but we also have a move function where we're saying this dot x plus equals 0.5. So whenever we call move, it will move the ball, the x value of the ball, 0.5 more. And our display function here is responsible for drawing where the ball is. And so it draws at this dot x, this dot y, this dot size. Right, so it's using its internal variables to manage where it moves. Great. So now the function, it can move itself and it can draw itself. And it knows where it should go and it knows how big it should be. Right? So all of this stuff is contained within this one object. And it makes it quite powerful. And it really simplifies this code, right? So here we have let ball equals new ball with our parameters 0, 150, 50. We make a canvas. In our draw function, we set the background. We say ball.move, call that function. Ball.display, call that function. And it works. And we have a ball that displays itself and moves itself. Half a pixel every frame. All right. So I've been trying to make a case for you today that arrays and objects will make your more complex programs, your ideas more powerful, more realizable. So here you can do more things, more complex things, a bunch of balls at a time, a bunch of balls in an array, a bunch of cubes falling through portals. You can use arrays and objects together to make something you couldn't have made before, or at least not made easily. There's before, without using objects and arrays, you couldn't have made it like an unbounded number of cubes falling through portals and turrets falling through portals. But when you use arrays and objects together, you have a lot more power. You can scale a lot bigger. You can do more grandiose things. You can make an entire particle system of sand, like the Rings of Power introduction. Right? There's no way they would make variables for each one of those bits of particles that they were modeling. The sand to make rings and Balrogs and whatever they make in that introduction. But if each one of those sand particles are a value in an array with some properties like their location, their size, their momentum where they're moving, each one of those has its own little model inside of itself. Then you can start scaling it up and putting a whole bunch of those things. Each one of those things has the context to manage itself, and it makes the code a lot cleaner. It makes this big, almost impossible Herculean task more easier to approach because now you found a good knowledge representation for it. A good, more powerful data representation for it. Okay. Whew. We got here. 5 minutes left. You probably have some questions. You may understand a little more, but I also added a lot more things onto the pile. Welcome to college. What do you think? Any questions? Concerns? Ideas? I know, you're not a class to talk out loud. I get it. I get it. So let's take a look at the sprout example again. And maybe this will make a little more sense. So here, just to refresh your memories. We have this little flower that we can grow. Now the flower in our world is its own self-contained thing. The flower, the seed here that grows into a flower is a class. Right here. And this flower, it takes an X and a Y value wherever we want to put it, wherever we want to plant the seed. And it also records the time, the millisecond timestamp when we planted it. So it can start growing at that time. And then we have the plant has a draw function. So when we call seed, it has a draw function. So when we make a new seed, it'll run all this constructor code, but then it also will have inside the object, it'll have this draw function that you can use as well. So this draw function turns off the stroke, starts first sprout, which we can see down here. First sprout, we start working towards drawing the first seed, the first bit of growth. What we do is we want to see what stage of growth we're in. So we're just simply taking the amount of time that's passed since we planted the seed in milliseconds. So every 1,000 milliseconds is 1 real second, or one real second, all real seconds. It was 1 second. And we divide that by 100. And then we take the floor of that, so we chop off the remainder. So now, through this we know through stage, if it's between 0 and 1 second, stage will be 0. This is between 1 and 2 seconds, stage will be 1. Between 2 and 3 seconds, stage will be 2. Between 3 and 4, stage will be 3. Between 4 and 5, stage will be 4. And past 5, stage will be 5. So we have a way to do 5 stages of growth, where each stage is 1 second. You can make the stages of growth 2 seconds by changing this to 2,000. We won't do that for now. And so now we've determined what stage we're in, so how many seconds has elapsed. We want to draw something different for each stage. So first stage, we just want to draw a seed. Second stage, draw first sprout. Stage 2, draw first leaf. Stage 3, big sprout. After that, draw the full flower. And each one of these are functions inside of the seed class. right? All the way to our big sprout, and finally our flower, which is a little more complicated, right? Where we do some pushes and pops and translates, all the good stuff. And so now we have this like seed, which the seed class, which has all this complicated stuff in it, right? Now let's see how we use it. So up here, we have our canvas. We set our canvas size to 600, 600, background to 0, so it's black background. Our seed, we have our seed variable that we've started here with let. We give it a new capital S seed with 600, 600, which is the with 300, 300, which is the location. Right. So now what this does is it uses this seed blueprint, this seed cookie cutter, to give us a new object. We made it either a house or a cookie. Right. We've made something from a pattern, a version from a pattern, a description. And so now we have the seed. And so now all that we have to do is in our draw function called seed.draw. And then the seed will manage itself. It'll grow itself. And what you could do is you could change this to have like an array of seeds. And then you could use that code that we took from placing the portals, and you could place a seed at mouse X and mouse Y. And just go through a loop and make sure you call draw all of them every update, and you can have a whole bunch of seeds draw on the screen and sprout into flowers, each with their own timer. Right, so this, hopefully now I've expressed to you that there is some power in objects and classes and arrays that you can then use to make your projects bigger and better. I'm sure it's a little intimidating now, but we still have 5 weeks of class left. Well, I mean, you're going to learn a lot independently, I'm sure, when you study for the midterms. But now we're in the stage in the class where we're building basic concepts. We're pushing your brains, giving you new tools. But then we're going to spend 5 weeks developing that toolkit and building more interesting things and learning more about this space. So you're at a spot right now which is rough, where you've learned a bunch of things, your brain is probably full, you haven't fully grasped things because you haven't used them a lot. Well, we're going to spend the rest of the class like developing, like growing the seed that we've been planting for 5 weeks. Okay. It is 4:30, 3:31. Leave if you have to. I will take questions if you have any. If not, good luck. I will send out information about study guide. I will send out an announcement about office hours. I will send out an announcement about the new due date for assignment 3. And I will decide on the actual timeline for assignment 4. But you have it to look at in the collection, the assignment 4 collection, and the openprocessing.com classroom. All right. Thank you all.